Now, I want to prove that every rational number, every fraction of integers, when we do long division to it, it will turn into either a finite decimal or an infinite repeating decimal. My first example is going to be 37 divided by 7. Now, you know how long division goes. 7 goes into 37 5 times. And then you're supposed to figure out 5 times 7, which is 35, and then you subtract, and you get a remainder of 2. Now, if you don't want to write remainders, if you want to write the decimal number, you extend the fraction bar, you write a decimal point, and you add some zeros so that you can drop a 0 and keep going. But I want to pause here and ask a really important question, which is really the key to this whole proof. Take a look at this 2. What other possibilities were there for this number? What can the remainder possibly be? With 37 divided by 7, you always get a remainder of 2. But what about 38 divided by 7? Then we would have gotten a remainder of 3. For 36 divided by 7, we would have gotten a remainder of 1. And for 35 divided by 7, we wouldn't have gotten any remainder at all. In fact, you might get 0, 1, 2, 3, 4, 5, or 6. But if you were getting a remainder of 7, then you messed up. That's not how long division works. You're never supposed to get a remainder that's bigger than the number that was in the denominator. So there are only 7 different possibilities for this remainder, and that's going to be really important going forward. So back to the problem at hand. You drop your 0, 7 goes into 20 twice, 2 times 7 is 14, remainder of 6. You drop a 0, 7 goes into 60 8 times, 8 times 7 is 56, remainder of 4. Drop a 0, 7 goes into 40 5 times, 5 times 7 is 35, remainder of 5. And it looks like I'm going to need some more zeros. Drop a 0. 7 goes into 50 7 times. Multiply, subtract. Drop a 0. 7 goes into 10 once. Multiply, subtract. Drop a 0. 7 goes into 34 times. Multiply, subtract. Drop a 0. Now I'm somewhere cool. Do you see how I have a 20 there? I have a 20 right here. And I've had a 20 before. And so my next number is going to be another 2, just like before. And when I multiply, I get 14, and then I'm going to get a remainder of 6, and then I'm going to drop a 0. So all of a sudden, I'm in like deja vu land. Like we're going to be repeating this same sequence of 6 numbers, 2, 8, 5, 7, 1, 4, over and over again forever. Now, when we're looking at the remainders, after a remainder of 2, when I do the process again, I'll always get a remainder of 6 next, right? Because when you had a remainder of 2, then you drop the 0, 7 goes into 20 twice, you get 14, you subtract, and then you get this remainder of 6. After the remainder of 6, you're always going to get the remainder of 4. That's always going to happen. After the 4, you're always going to get a remainder of 5. And after the 5, always a 1. After the 1, always the 3. And then after the 3, always the 2. So that's another way of looking at this pattern of 6 digits. The remainders repeat, therefore the digits that are up here will repeat. So now what happens if we were doing a long division and the remainder were equal to 0? So for example, if I want to compute 78 divided by 4, well, first, 4 goes into 7 once. And so in the tens place, I'm going to put a 1. You multiply, you subtract, you drop the 8. 4 goes into 38 9 times. You multiply, you subtract, you get a remainder of 2. So we need to get out the decimal points so that we can drop a 0. And we find out that 4 goes into 25 times. And then when you multiply, you get a remainder of 0. And you think that's really weird, but it's not weird at all. You actually get to stop, right? That's how long division works. So if you ever get a 0 as a remainder, you stop dividing, and then you know that your rational number was actually a finite decimal. That's actually great. That's easy. But going back to our original problem of 37 divided by 7, you're never ever going to get a remainder of 0. However, the repeating decimal expansion can't possibly be 7 digits long because there were only 6 possible remainders. You never get a remainder of 0. There are only 6 possible remainders left. And so you know that you are going to get a repeating pattern of numbers that's 6 digits long or fewer. And if this sounds familiar, it really should. If you only have 6 possible remainders, but you have a decimal expansion and if you worked out 7 digits of it, well then 2 of those digits have to match, right? Which means you have to start repeating your decimal expansion. And that is absolutely the pigeonhole principle. In any case, there are only 2 possibilities. When you divide integers, you are either going to get a finite decimal, we don't know how long, but the decimal expansion may terminate, or you could get an infinite repeating decimal. Either one is fine.